Okay, this is going to be one of the most interesting videos that I've done on any of this so far, and it just keeps getting more and more interesting. So we're going to talk about pi, we're going to talk about the golden ratio, we're going to talk about the fine structure constant, gravity, speed of light, dark energy and the cosmological constant, the Higgs boson, and redshift, as well as Einstein's equations and general relativity. So I'm just going to jump right in and start explaining how this all works together. You should watch previous videos so that you can kind of see the process on how this has been evolving. This is still very much a work in progress. The graphic that I'm showing you right now is not complete. I have a lot of orbits left to calculate and add to the data set that I have on these orbits. So just you're gonna have to bear with me on that. It's actually quite a bit of work, and I'll explain why. So most of the work involves this area which I call reversals. What ends up happening is we calculate a single orbit by the amount of steps it takes to get from here all the way around the circle to here. That's what this graphic is representing. Okay. If we go on the negative side, the first orbit is 2 pi. What I mean by that is, let's just go back up here and take a look at, we're set at 0 for C right now. So if we look at our angle, right, between the fine structure constant and the golden ratio, right, we have 4.7 degrees. Or sorry, 0.474 degrees. Um, so from there, if we move through our orbit in the negative numbers, right, what'll happen is we'll get here, it'll be exactly pi. So half an orbit, not quite, it's actually just under half an orbit because we're starting here. But half the circle is exactly pi. And then when we move the rest of the orbit around to get to the 0 mark here, we're at exactly 2 pi. So right off the bat, that's a really, really interesting behavior. But then it gets faster. The orbits get faster and faster and faster, as represented in this graphic. Now, the size of these circles is representative of the speed at which the orbit takes place. So you can see that we're getting faster and faster and faster and faster and faster. And then we do finally start to decelerate before we end up getting into this zone and this zone, which I'll talk about as we in a little bit here. Um, so we've got this acceleration and deceleration happening. I'm literally counting and calculating the orbits manually. I'm doing that because I want to be able to see little, little fine behaviors that we might not otherwise see if I just wrote a program and calculated it and ran counts. And part of that is showing itself with a couple of interesting things to note. So when we get into this reversal section, so what is this? I have these different phases set up. So I have convergence, convergence, deceleration, acceleration, deceleration. It's all kind of broken up into phases. And that's exactly what happens. So when we go to the positive numbers, we make one revolution at 847,698 steps for one complete revolution, one orbit. From there, it never quite makes the second orbit. It seems to converge on -10. And what I mean by -10, this angle, which starts off at the fine structure, the golden angle minus the fine structure constant as an angle, that value will, traverse to basically become -10 or converge to -10, okay, on the positive side. On the negative side, it does the exact same thing and converges on the same thing, -10. Only it's not quite -10 like on the negative side, it stays above 10 but never hits 10, never hits that -10. Whereas on the plus side, it stays below -10 but never hits -10. It just keeps converging toward -10 on both sides. So it's got a symmetrical behavior there, even though you've got this acceleration, deceleration, reversals phases in the negative side only. Now, in the reversals, what I mean by that is, so we'll be orbiting this way, for example, counting the orbits, and then randomly it'll just pop and start going the other direction. Now, I'm not sure how many of these reversals there are. This is going to be, again, I've only calculated 31 of these revolutions so far. So these reversals, I'm not sure the frequency of reversals that there are, but we will get to a conclusion there. We will have an answer, and this graph will be a complete graph showing basically the acceleration and deceleration. Now, I had mentioned early on in my research that I posted with this as I was discovering it, that this seemed like it was dark energy, like or seemed to suggest that there was a mathematical explanation for dark energy, not just a cosmological constant or some unexplained force that we don't understand. And this seems to lend itself to that theory. So if we look at Einstein's equations, we have the Einstein equation for general relativity, and then we've got the second Feynman equation, and we're looking at the cosmological constant and pi. Now, I stipulate, based on what I'm seeing with this graph and with this behavior, that what we're seeing is a consequence of us using a static value for pi. Now, what we accept is pi, and with these infinite series equations that calculate the pi to the trillionth decimal place. This is problematic and creates situations where we can miss things, um, because things aren't static like that. So what I think happens is, if we take out the what we call the cosmological constant, just simply take it out and replace pi with psi pi, I'm pretty confident that that's going to be a more accurate way to represent what's going on. Now, again, that's not verified. This is just kind of loose theory based on some very compelling and logical, results that can be repeated and calculated by anybody on the planet. So there's investigation that needs to happen there, as well as with the Higgs boson and with the redshift, because the curves are very similar. And all of these equations, whether you're talking about general relativity, whether you're talking about quantum mechanics, so many equations use pi, and we treat it as a static value. And in doing so, we set up potentially conditions where we're going to miss things. Okay, so just to kind of summarize, we do see some very interesting correlations here, but none of this is absolute proof. I just think it's very compelling and striking, and suggests that yes, this is very strong evidence that we've missed something as far as pi is concerned, as far as all these constants are concerned. There's some definitely mathematical behaviors that you can find in the numbers themselves, rather than having to measure and build billion-dollar pieces of equipment to measure the universe. Not to say that that isn't useful, because we obviously need to confirm a lot of experiment, confirm a lot of theory and whatnot. But at the same time, a lot of focus could be put in mathematical modeling and mathematical discovery, which could make our experimentation a lot more efficient, and explain things a lot more in a lot more sensible way. I think that this is really, really, really fascinating stuff. Now, the last thing I want to note before I end this particular video is, in the growth, or in the acceleration and the deceleration end of the negative side. So we have starting here and starting here. So this is this, and this is this. There's these weird little bumps, and they're not errors. There's only two that I have so far, with the exception of in the middle, where the reversals is really chaotic. Um, but there's these two bumps on either side. And again, I've checked and checked and double checked and triple checked and quadruple checked, and they are not errors. So there seems to be a point in that acceleration, just as it reaches kind of a more stable and uniform acceleration, even though it's still kind of growing and then accelerating. It's definitely slowing down in that, but it's like almost like a marker where it just kind of slows down briefly and then speeds back up briefly. I don't know if it's like a kick to get it over the hump. I'm not sure. Um, but either way, those are not errors. Those are two little bumps, and I've yet to put a name on them yet, because I don't know what they are. But as I figure this stuff out, you can bet that they'll have. I'll try to describe as much about them as I could possibly find, at least. So there you have it. I mean, I don't know. I don't know how else to express the interest of this. Like, just the mathematics of it is very simple compared to a lot of Einstein's equations and whatnot. And I'm not saying that we have to replace or get rid of any of that, but I'm saying that all the equations that we use that involve pi, we seriously need to reevaluate those equations, and any errors that or corrections that we're making to those equations, that could be potentially because we're using a static value for pi, and we're treating it as a constant that this doesn't change. It has a single value and doesn't change no matter the scale. And that's where I think the logic fails. right? I think what this proves more than anything is that pi is definitely a scalable number. It's no one particular value. Now we see it a lot as the 3.14, but it doesn't turn up exactly like that if you think about it. Every time we measure it, every time we check it, it's always kind of this approximation. You never get the exact. You only get the exact if you have a supercomputer that calculates trillions of digits. And, we say it doesn't matter because it's only approximate, but clearly there's some pi behavior that we don't understand. So thank you. And again, don't take any of my word for this. Try it yourself. It's all available for you to take a look at. Thanks.